Hello and welcome to yet another video of Cornerstones of Math, and welcome to yet another integral video. Let us take a look at the problem first. Problem A says calculate three areas A1, A2 and A3. So these three areas that are enclosed by two curves y equals a cosine x, where x is from 0 to pi over 2. So this curve y equals b sine x, where x is from 0 to pi, which is this curve shown in the figure, and x and y-axis. Here, a and b are some positive constants. The next problem says, prove that area A2 is less than area A3. And the third problem says, on the first quadrant of the AB plane, indicate three regions where point A, B satisfies these conditions. Alright. Let's start with the first one. In order to calculate the area, the first thing we need is the x-coordinate where two curves intersect. Suppose that two curves intersect at x equals alpha. Then from a cosine alpha equals b sine alpha, we have sine alpha divided by cosine alpha equals a divided by b. So we have tangent alpha equals a over b. So alpha is whatever value between 0 and pi over 2 that satisfies tangent alpha equals a over b. Now let's move on to the calculation of areas part. Let's start from area A1. Obviously, the area is given as the integral of a cosine x minus b sine x, where x changes from 0 to alpha, our intersection point. So the integral is a sine x plus b cosine x, 0 alpha, which gives a sine alpha plus b cosine alpha minus b. So we require values of sine alpha and cosine alpha. Here, since a and b are both positive and alpha is in between 0 and pi over 2, we can simply draw a right triangle with base b and height a, and this angle right here is alpha, so that tangent alpha equals a over b, which we have previously obtained. Then the length of the hypotenuse is square root of a squared plus b squared, so we have sine alpha equals a divided by square root of a squared plus b squared, and cosine alpha equals b over square root of a squared plus b squared. Therefore, area A1 is given as a sine alpha equals a squared divided by square root of a squared plus b squared, plus b cosine alpha equals b squared divided by square root of a squared plus b squared, so this minus b, which simplifies to square root of a squared plus b squared minus b. Next, area A2. Here we have to divide into two intervals. From 0 to alpha, we integrate b sine x, and from alpha to pi over 2, we integrate a cosine x. So we have minus b cosine x, 0 alpha, plus a sine x, alpha pi over 2, which gives minus b cosine alpha plus b plus a minus a sine alpha, and using the expressions for cosine alpha and sine alpha, we have minus b squared divided by square root of a squared plus b squared plus b plus a minus a squared divided by square root of a squared plus b squared, which simplifies to a plus b minus square root of a squared plus b squared. Finally, area A3. Here, let us use the subtraction of areas. First, we integrate b sine x from x equals alpha to x equals pi, and that gives the area under this part of the curve. Then we have to subtract this area, which is an integral of a cosine x from alpha to pi over 2. So you carry out the integral, which gives, and using the expressions for cosine alpha and sine alpha, we eventually obtain b minus a plus square root of a squared plus b squared. So we have calculated the areas of all three regions. Now, what was the next problem? To prove that area A2 is less than area A3. This is quite obvious from the figure actually. If we split the graph of y equals b sine x, the left half and the right half have the same areas due to symmetry. But this bit right here belongs to area A3, so A3 is obviously larger than A2. But if you do not like the comparison between areas with your eyes in this integral video, you can always use the results of the integrals to prove more algebraically. So using these two, A3 minus A2 is given as A3 b minus a plus square root of a squared plus b squared minus A2 a plus b minus square root of a squared plus b squared, which simply gives 2 times square root of a squared plus b squared minus 2a, and this square root of a squared plus b squared is definitely greater than square root of a squared, which is just a, so the entire thing is greater than 2a minus 2a, which is 0. Therefore, we have the conclusion that A3 is greater than A2. Now let's move on to the interesting last problem. On the first quadrant of the AB plane, indicate 3 regions where A, B satisfies these conditions. Now let us start with the first condition. Here, this A2 is less than A3 is always true because it is what we have just proved in the previous problem. Therefore, we only have to look up for the condition for A1 being less than A2. When this inequality holds, A1, so square root of a squared plus b squared minus b is less than A2, so a plus b minus square root of a squared plus b squared, which simplifies to 2 times a squared plus b squared is less than a plus 2b. Since both sides are positive, we can square both sides. Yeah, you need to remember that we can do this only because we know that both sides are positive. Then we have 4 times a squared plus b squared is less than a squared plus 4ab plus b squared. So we have 3a squared is less than 4ab. And since a is positive, dividing both sides with a preserves the direction of this inequality sign. So we yield 3a is less than 4b. So b is greater than 3 over 4a. This means above the line b equals 3 over 4a on the AB plane. We will summarize the results later, so let's move on to the next condition. The second condition, A2 is less than A1 and A1 is less than A3. The condition for A2 being less than A1 is simply the condition obtained in the previous case, but the direction of the inequality is switched. That is, b is now less than 3 over 4a. So we have this, and now for the condition of A1 being less than A3, which means square root of a squared plus b squared minus b is less than b minus a plus square root of a squared plus b squared. So this term and this term cancel out. So we just have b is greater than 1 over 2a. And the common range between 1 and 2 gives b is greater than 1 over 2a and less than 3 over 4a. And for the third case where A2 is less than A3 and A3 is less than A1, since this part is always true, which we have proved in problem B, we only have to find the condition for A3 being less than A1, which is what we have obtained in the previous case with the direction of the inequality switched. That is, B is less than 1 over 2A. To summarize, the regions obtained in 3 cases, which are these, are indicated in this figure. So these are the 3 regions, and 2 boundaries, which are lines b equals 3 over 4a and b equals 1 over 2a, are equivalent to the condition a1 equals a2 and a1 equals a3 respectively. And that was all for today's video. Thank you all for watching. Please don't forget to hit the like and subscribe buttons, and I will see you in another video.